So good morning all. In the last class, we started with the phase controlled converters. So rectifiers, that is the phase controlled converters, are rectifiers using thyristors. Rectification is a process of converting an alternating current or voltage into direct current or voltage. That is, rectifier converts AC to DC. So here we are able to converting, that is AC into DC in a controlled manner. Okay, you can see here the types of rectifiers in the. Okay, so that is it is going to be a single phase and a three phase. So in that we will be having uncontrolled, half controlled and fully controlled in both three phase as well as a single phase. So in uncontrolled, so we have off wave and full wave. So that is, again we know this, uncontrolled means we'll be using only diodes. Okay, and off controlled means mixture of diodes and thyristors, and fully controlled means we are using only thyristors. Okay, uncontrolled and off controlled. So the rectifiers, they're going to be from AC system to load. Again it is going to vice versa. So that is from DC to back to the source, that is a AC source. Okay, so you can, next we will move on to, so this is what, that is a three phase and a single phase. So we have a two circuits here. So that is single phase, you can see here. So this is a single phase, what, that is a single phase, that is a one line is going to be active and that is given to the load and it is going through, this is a neutral. So next in a three phase okay, so in a three phase, so in a three phase here, so that is we have two active lines, that is a phase 1, phase 2, phase 3, and they are entering to the load and they are moving to the one neutral line. Okay, so coming to this here, this circuit, you can see the single phase is going to be this one, and a three phase you can see here. So we know this, that is wave is going to be vary from, that is one cycle, we are going to say this is going to be one cycle, that is 0 to pi. So that is 0 to 180 degree. Okay, one cycle is going to be a 0 to 180 degree, that is, sorry, 360 degree. Okay, this is going to be a half cycle. So we are going to say, so this is 0 to pi is going to be a positive half cycle, we will say, and pi to, so that is a 360 degree, we are going to say it is going to be a, that is a negative half cycle. So one cycle we are writing, that is, this is one cycle is going to be, so 0 to 360 degree. So coming to this three phase, you can see here we have a three phase, that is the three signals. So red is going to be a phase 1 and yellow is going to be a phase 2 and the blue line is going to be a phase 3. So this is a three phase and a single phase. So single phase supply is enough for our home appliances, and the three phase supplies, it is needed for the industries, that is the large industries. Okay, and factories. So next we'll, so we have seen, that is the quadrants. So that is a phase control converters. So to provide either maybe it is one quadrant or two quadrant or a four quadrant. So thyristors and diodes. So it is going to be a, so one quadrant. So rectifier, the converter. And so if I'm having only thyristor, it is going to be a two quadrant. So that is, thyristor is a, or SCR is going to be a fully controlled device. So it is going to be the power, the flow of power from AC system to the load as well as vice versa. So that is, so power is going to flow from DC to the AC also here. So this mode we are going to, that is a power flow from DC to the AC, we are going to call as a inverter in our inverting mode. You can see for the rectifier, we have a rectifier first quadrant and inverter, that is for the fourth quadrant. So rectifiers are going to be, or thyristors are going to be two quadrant converters. So next, if I'm using a two thyristors or two SCRs, so we'll be having, that is all the four quadrants. So that is one SCR will take a two quadrants, and if I'm going to connect the two SCRs back to back, it is going to cover the four quadrants. So these are going to types of a phase controlled converters. And coming to the control techniques, we have three control techniques here. That is a phase angle control. It is also called a firing angle and extinction angle control and a pulse width modulation control. So that is, this is a, so circuit, it is going to show the technique of a controlled conversion from AC to DC for off wave rectifier, which uses unidirectional switch. That is a switch you are going to use. The switch can be, here we can use, so it may be a that is a control to me, that is a unidirectional. So and it can be a, that is a diode, and it can be a the device, the switch is going to be turned on, and it going to conduct the current in the direction of the arrow it is shown. Okay, so maybe switches we are going to be, we will be having a pulse triggered switches and a level triggered switches. The pulse triggered switches are going to be SCR and GTO, and level triggered switches are going to be BJT, MOSFET as well as IGBTs. Okay, so coming to the phase angle control technique, you can see that is the phase angle or firing angle means, so that is a sine wave will be given at the input, that is a ES is equal to EM sin omega t, that is going to be input or AC signal. Okay, for that if I'm going to apply pulses, so then the SCR is going to be turned on. You can see here, so this what we are having this portion, so here that is this portion of the waveform, or that is this portion what it is shown is a 0, that is a load voltage is going to be 0. So why SCR is not turned on? That is input is started from the reference 0. Okay, so it is not turned on. Where I am applying a pulses, that is where I am applying pulses here. So there at an angle alpha. So at an angle alpha, I am going to apply pulse. So then that pulses are given to the gate terminal of the SCR. So then SCR is going to be turned on, and so then V naught is equal to, you can see that is V naught, that is a load voltage is going to be a input voltage. So here your V naught is equal to VL is equal to, so ES, that is a supply voltage. So that is for SCR. So next we have a level triggered, so they are going to be BJT, IGBT, so they are going to be continuously, they have to give a signal to the, so thyristor to turn on. Okay, so that is the way how much the load voltage it is covered, up to that we will be giving the control voltage. So when you are going to use, that is a BJT, IGBT, MOSFET. So this is here a firing angle, we are going to represent as alpha. So alpha, it is going to be firing angle, it is going to control the turning on of a thyristor. Okay, so this is going to be a, no, that is a phase angle control or firing angle control. That is angle at which the thyristor is entering into the on state is the firing angle. So depending upon the angle, so that is it is going to be turn on of this device. So these converters during the positive off cycle, when I'm going to apply gate signal to the SCR, so thyristor is going to be turned on. During the negative off cycle, we will supply the reverse voltage, thyristor is going to be turned off. This kind of commutation is called a natural commutation. These are also called a, that is a line commutation. So next we will move on to, so extension angle control. So this is shows that is the input voltage, it is given as sine wave, and output voltage it is a low duration, that is the pulse, that is a ARs and GTO, and well triggered is a UJT, BJT. Here the load voltage EDC, you can see here it is start from this, and that is the device is turned on, and it is going to follow the input voltage. So when you are going to apply this pulse triggered so inputs, so that time, so it is going to be, so voltage is going to be 0. Okay, so that is the control pulses for the level triggered and the pulse triggered switches we have seen, that is okay, C and D. So rising edge of the control pulse coincides the beginning of the input voltage waveform. So the falling edge so lies at a controllable angle pi minus beta. Okay, this is going to be a pi, so and so this duration is a beta and this is pi, and the duration this is going to be a, where the load voltage is appeared, so that duration is going to be pi minus beta. Here the angle beta is called the extension angle. In a pulse triggered switch, the control pulse consists of two short lines. So one is for turning on, another is for the forced turn off. Okay, so that is the two lines we'll be having. That is one is for turn on, another is going to be for a turn off. So this is what extension angle. It is beta. It is going to be an extension angle control. So next is the pulse width modulation control. You can see here, so here also we are going to, that is a turn on pulses and turn off pulses are there, and both are going to be a pulse trigger. So pulse width modulation means, so width of the pulse is going to be a modulated, that is it is going to be varied. So that is if this is going to be a pulse, so this pulse, so if this is going to be width is going to be a T, so this pulse width is going to be a varied and it is going to be modulated. So this is one of the modulation technique, and using varying, just a minute. Okay, so this is the way, this is the, by varying the width of the pulses, we are going to control the turning on of the device. So this is the pulse width modulator. Here, this is the pulse width control parameter is the tilde. Okay, so you can see the firing angle alpha, that is a firing angle control. So at what angle that is the thyristor is going to be, that is turn on, that is angle is 15 degree, or this is going to be a, so 45 degree, that when I'm going to apply the pulse signals to the gate terminal of the SCR, that time the SCR will be entering into the on state. So this is the firing angle alpha. Okay, next is a beta. So this is extension angle, and this is a tilde, this is a pulse width control parameter. So these are the different techniques. So our control techniques of that we are going to use in, so phase controlled. So we are going to discuss that is a single phase controllers or converters. So first we will move on to that is a single phase off wave control rectifier. So that is a rectifier, that is a single phase off wave control rectifier. So that is going to be with the resistive load as well as with the inductive load. So that is we are going to discuss that is a single phase off wave control rectifier. So that is it is going to convert AC to DC. So we are going to discuss the two. Load is going to be a purely resistive, another is going to be a load is going to be highly inductive. Okay, first we will go with the, that is a single phase off wave control rectifier with the resistive load. You can see here that is a single phase supply is given, okay, for the primary of the transformer, and the secondary of the transformer where that is E is equal to Em sin omega t is available, and that is given to the thyristor, and the load is going to be a resistive. Okay, so and that is a, we are giving a AC signal, and across the load we are going to get a EDC, that is a DC voltage. So how we are going to get this voltage? You can see the waveform here. So during the positive off cycle, so already I told the single cycle is going to be a 0 to 2 pi, and during the positive off cycle means from 0 to pi. During the positive off cycle, so we are going to apply pulses, that is the firing pulses. You can see IG. So firing pulses we are applying. So where I am applying the pulses, so then so this is thyristor is going to be turned on. So during the positive off cycle, when I am going to apply, anode is made positive with respect to the, that is the cathode is connected to the load. So then for the gate I'm going to apply pulses, that is the firing pulses to the gate terminal of the SCR. So then SCR is going to be turned on. So then I'm going to get V0 is equal to, so you can see it is going to be V0 is equal to, or EDC is equal to what? So ES only when SCR is turned on. Next, when I'm going to apply the reverse voltage from the period pi to 2 pi, that is a negative off cycle. So SCR is turned off. So then V0 is equal to, or EDC is equal to what? 0. Okay, so this is the waveform, that is the load voltage EDC it is given. So that is when I'm going to apply pulses at an angle alpha, so that time the SCR is going to be turned on, and it is going to converting the AC signal into a DC. Okay, so you can see that is a load current IDC also here. So this is IDC. So just EDC, IDC is equal to what? V by R, that is EDC by R, that I will get it. So next, voltage across the SCR. So voltage across the SCR, we know this. Okay, so when SCR is turned off, so where SCR is turned off, this is, so this portion is what is there, SCR is turned off, and this is the portion the SCR is on condition again. So for this portion SCR is going to be off, and so this is the portion SCR is going to be on. Okay, because it is a positive off cycle, I'm getting the output only in the positive ops. Okay, when I'm going to apply the reverse voltage, so it is SCR is turned off, and V0 is equal to, VL is equal to, our EDC is going to be 0. So when I am going to apply the pulse, so next from that is a 2 pi to 3 pi. So when I'm going to apply the pulse, so that is when I'm going to apply the next pulse between that is 2 pi to 3 pi, again SCR is going to be turned off. You can observe alpha it is given. So for each end, that is a positive off cycle. So this is how we are getting this. This is thyristor, right? So this is thyristor. This is a controlled manner. So it is going to work. So depending upon the that is where I'm going to apply, at what angle I'm applying the pulses to the gate terminal of the SCR, then SCR is going to be turned on. So this is in a controlled manner, it is going to turn on, then it is going to converting the AC signal into DC signal. So in the normal diode, how we are going to get? So instead of this SCR, if I use a normal diode, so how we are going to get? This is going to be your input signal. So then I'm going to get the output signal like this. Okay. Okay, so it is like this. So it is uncontrolled manner we are going to say. Okay, here also that is AC signal is converting into DC. When I'm going to use a normal diode, this is in a uncontrolled manner. So here where I'm going to use, so that is a thyristor. Okay, so it is going to be a controlled manner here. So you can see here during the positive off cycle we will apply pulses and we will get that is a EDC, that is a load voltage, so across the resistor, and so current can be converted, so that is, so IDC is going to be what? So EDC divided by R. So okay, so then voltage across the thyristor, we know this, when the thyristor is turned off, voltage across the thyristor is going to be high. So when the thyristor is turned on, voltage across the thyristor is going to be low. So you can see here voltage across the thyristor when it is turned off, it is equal to its input voltage. So when thyristor is turned on, voltage across the thyristor is going to be 0. So that you can observe in the waveform. So again, it's a problem with your syllabus, that is a third semester syllabus. So because here, if you have remembered, that is a rectifier with a normal diodes, we will be having the calculating of average value of the load voltage, that is EDC, IDC, and high RMS, ERMS. Okay, so here also these analysis are there, but according to your syllabus they are telling that there is no analysis, only circuit and explanation, but they're asking problems in the examination. So in the last question paper they asked the problems on rectifier, so I will just give the, that is I will just briefly explain the, that is formulas, and as well as also that is I will briefly explain the problems. So it becomes a very vast for us to cover the circuit and a circuit as well as the analysis of the circuit, so deriving each and every expression. Okay, so this is average load voltage. The average value of the load voltage can be derived, that is EDC. I am going to get EDC, that is EDC is equal to, so that is, so 360 degree means it is going to be a 2 pi, 1 divided by 1 pi, and it is going to be what? The conduction, that is alpha to pi, that is a conducting of a thyristor, alpha to 180 degree, and so ES, so this ES is what? So this ES is equal to EM sin omega t. Okay, so it is d omega t we have to write. Okay, so EDC, that is average value, is equal to, you have to take a full cycle, that is one cycle is, so 360 degree, it is going to be 1 divided by 2 pi, and conduction of the thyristor alpha to pi, it is conducting for a period of alpha to phi, and we have to integrate that input voltage ES, here ES is going to be EM sin omega t. So integrating of this, I'm going to get EDC value. Okay, understanding? So I am going to take, so that is, so this full cycle, that is 1 by 2 pi. EDC is equal to 1 divided by 2 pi, and this is the conduction of the this one. This is alpha and this is phi. The conduction of the thyristor, the period. So that I'm going to integrate. For that period, I'm going to integrate the input signal ES. ES is equal to EM sin omega t. So this is just a waveform of, that is, it is belong to the first quadrant. You can see here that is a EDC or VDC is going to be one and the same. And so that is when I'm going to integrate it. So I'm going to get, so this is, so VM, that is VDC here is nothing but your EDC. In one textbook they will mention as a EDC, in another textbook they will mention as a VDC. E and V indicating the voltage only. Okay, so here integrating this is we are going to get VDC or EDC is equal to VM by pi. VM is a peak voltage. So if you have gone through your circuit analysis, that is electronic devices lab, so we are going to write that is a sine wave like this, and this is going to be a VM, that is a peak voltage, and this is going to be a minus VM. Okay, if it is going to peak to peak, that is we are going to write V peak to peak, it is going to be, so 12 volts if I'm going to say means, so this I'm going to represent as a 6 volts, and minus it is going to be another 6 volt. 6 minus of minus 6, I'm going to get a 12 volt peak to peak. Upper peak, that is a positive of, is going to be plus 12 volts, and the negative peak or negative off cycle is going to be another 6 volts. So 6 minus of minus 6, totally it becomes a peak to peak of 12 volts. So VM peak voltage, so that I'm going to take, that is a 6 volts only here. If in the problems, if they are going to peak to peak voltage. Okay, so then I'm getting the VDC or EDC is equal to VM divided by 2 pi 1 plus alpha. Here if alpha is equal to 0, I'm going to get, so VM, so it is going to be alpha is equal to 0, so that is cos 0 is going to be 1, so 2 will get cancelled. I'm going to get VDC is equal to VM by pi. So like this we have to calculate the VRMS values. So this is VRMS, you can see VM by 2 into 1 by pi minus alpha plus sine 2 alpha divided by 2 to the power of 1 by half. So according to the syllabus, we don't have this analysis or derivations, but you have to remember the formulas because they are asking problems on rectifiers. Some of the performance parameters, so that is those are going to be same as your normal diode expressions. Output power, that is output DC power is going to be PDC is equal to VDC into IDC, and output AC power PAC is equal to VRMS into IRMS, and efficiency of a rectifier, it is also called the figure of merit. So it is going to be the ratio of, that is PDC divided by, that is a PDC to PAC. Always we are going to express this efficiency in percentage. You can write this is going to be into 100%. So always you express this efficiency in terms of percentage. The efficiency is going to be PDC divided by PAC, and the form factor, which is the measure of shape of the output voltage, is, that is AFF VRMS divided by VDC, and the ripple factor RF is going to be square root of VRMS divided by VDC whole square minus 1. It is going to be equal to form factor square root of form factor square minus 1, and transformer utilization factor TUF, it is a PDC divided by, that is the VS into IS. So you have to remember the formulas, so at least to solve the problems. So here we have a problem, but I won't take this problem. I will take, this is another textbook problem. I will take the problem from the prescribed textbook. So here the first problem. Half wave control rectifier as a purely resistive load of R and the delay angle is alpha 5 by 3. Determine the efficiency, form factor, ripple factor, transform utilization factor and peak inverse voltage. That is a peak inverse voltage also. It is there. Peak inverse voltage for SCR T1. Okay. So efficiency PDC divided by PAC. So we have to calculate the DC power EDC square by R and the PAC, that is a ERMS, that is a E and B indicating the same, that is voltage. E square RMS we and divided by, it is R, it is not K, it is R only. Okay, so calculating those PDC and PAC, so we can calculate the, you can see here how they are calculated. EDC here, so EM divided by 2 pi 1 plus cos alpha, alpha is going to be pi by 3, so then we are going to get, so EDC is equal to, so 0.239 of EM. They are not given the peak voltage of the waveform. Then ERMS is equal to, so we have a formula for ERMS, EM into pi minus alpha divided by 4 pi and sine 2 alpha divided by 8 pi to the power of half. So alpha is 5 by 3 and ERMS is equal to 0.825 EM. So substituting this, so this we are going to get, so that is, so the peak voltage is not given in the waveform, so EM is the peak voltage, so then efficiency we are going to get 24.28%. So we calculated efficiency. So next the form factor ERMS divided by EDC, substituting ERMS and EDC we are going to get form factor in terms of percentage 203.3%. Then ripple factor, that is the form factors minus 1, that is the square root of form factors square minus 1, we are going to get in terms of percentage 177%. So next transformer utilization factor PDC divided by ES into IS. So ES and IS are the RMS secondary voltage and current respectively. So ES is equal to EM divided by root 2, IS is equal to ERMS divided by R. So then we can calculate, that is the transformer utilization factor. So peak inverse voltage is going to be a, that is a peak voltage, so EM. So in this way the problems will be there, so you need to calculate. Usually they will ask a problem, so regarding to calculate efficiency, form factor, ripple factor, so transformer utilization factor as well as a peak inverse voltage. So we have some other problems, so you can refer, I will share this and if you have a textbook also you can refer. So next we will move on to the next topic. Here also some problems are there, so you can calculate and you can try to solve these problems. This is solution is already there, you need to practice. So you take some values and try to solve the, that is how to calculate efficiency, ripple factor and form factor, that is a UTF and peak inverse voltage. So last time I didn't cover, I just covered whatever it was there in the syllabus, but in the question paper they are asking problems on rectifier also. So understood? Do you have any doubt? So in the circuit and the working of the circuit, so what we discussed, so this is, so of your rectifier. So it is going to be easy, but you have to draw the proper waveform. Okay, you have to draw the proper waveform. So thyristor symbol you have to write very properly. So instead the gate is not there means it is going to be diode only. So then your circuit is wrong. Okay, so you have to check it out. So that is your circuit is correct. You have written the thyristor symbol correctly. Okay, so then the waveform, so that is you applied pulses. Okay, so at what angle, that is thyristor will be start conducting, so that is alpha you have to mention. Okay, so you have to remember, that is because it is a off your rectifier and it is going to, that is we are using only one thyristor and it is going to conducting only during the positive off cycles. So like natural commutation, while applying a reverse voltage, so thyristor is going to be turned off. So you have to write the proper waveform and you have to write the proper explanation. So they won't ask derivation, they should not ask derivations on. So that is they are finding out the efficiency, derivation of efficiency, form factor and all. According to the syllabus, those are not there, but they're asking problems. So next, if you have any doubt, you can ask. Otherwise, I will move on to that is a single phase off wave control rectifier with the inductive load. So this we are going to call that is a single phase off wave control rectifier with a RL. So but here the load is going to be highly inductive. So do you have any doubt till now what I covered? So that is the control techniques also very important. You have to write the waveforms very neatly, and alpha is the firing angle and beta is the extinction angle, and the tilde is going to be the control parameter, that is a pulse width control parameter. So do you have any doubt? So I can move to the next to this topic. I can discuss this. You can write in chat or you can so unmute and yourself. You're understanding or you're following or you are just joined the class and your mobile or your laptop is somewhere and you are doing something else. So I will just one ask a question, that is a EDC I'm getting. So what kind of that is a wave it is? So rectifier it is converting AC to DC. So DC is a what kind of waveform what I'm getting? Is it a pure DC? You can write in chat. Is it what the rectifier it is converting AC to DC is going to be a pure DC or not? You are not going to talk, right? ಎಲ್ಲರೂ ಮೌನ ವ್ರತದಲ್ಲಿದ್ದೀರಾ? Okay, fine, no problem. So here, that is here the load is going to be highly inductive, and this we are going to call that is a single phase off wave control rectifier with that is RL load or inductive load. That is we have a resistance as well as inductance, but it is going to be highly inductive. So you can see for the primary of the windings, we are given AC supply, and secondary we are getting EM sin omega t, and that is given to the thyristor, and it is converting that is a so AC into a DC across the load. We are able to get a DC voltage. It is going to be pulsating DC. It is not a pure DC. So coming to the waveform, so we are applying a AC signal. That is the one cycle is going to be considering that is a 0 to 2 pi. And we are applying the gate pulses or a firing pulses at an angle alpha. Okay. So we are applying the firing pulses here at an angle alpha. So next the load voltage EDC, you can see here. The load voltage you can see. So it is going to be same as your previous one. When you are going to apply angle alpha, so thyristor is turned on. Okay, it is started conducting, that is EDC, and I'm getting the conversion of AC into a DC voltage. So at T01 from here to T1, so I'm getting this, but still the conduction is that is a current or voltage, it is so still going in the reverse direction from T1 to T11. So then from T11 to T2 0. So application of a reverse voltage, the thyristor is turned off. Again where you are applying, that is during the next positive off cycle, again thyristor is going to be turned on. So why this, that is this portion here, so that is it is the reverse. I'm applying a reverse voltage, you are applying a reverse voltage here, still SCR is not turned on. So voltage is flowing in the reverse direction. Why this is happening? Anybody will answer why this is happening? So inductor property is what? What it will store? Inductor. Anybody? So inductor is going to be a load now. So across the load we are getting a pulsating DC. But when so we know this, when we are going to apply reverse voltage to the thyristor is going to be turned off. So here, so thyristor is not turned off, but the voltage is flowing in the reverse direction. So you can see the current flow also here. So why it is happening? So here the load is going to be inductive and it is highly inductive. So during the negative off cycle, so that is a current continues to flow till energy it is stored in the inductance. That is during the conduction of a thyristor, energy that is storing in the inductor. So energy that is storing in the inductor, it should dissipate. So this is the time. So from T1 to that is at T11, so inductor is going to be dissipates its energy. So that is, so it is stored energy from the period T01 to T1. So then it should dissipate. So dissipation of that energy, it is going to take this in the period T1 to T11. So energy stored in the conductor. So due to the energy stored in the conductor, so current continues to flow up to the instant of T11. So at instant T11, the load current becomes 0 and we are applying a negative voltage, a reverse voltage, thyristor is going to be turned off. So according to that, we are getting the waveform. So I will stop here. I will discuss this circuit tomorrow again in the next class and how to. So that is what we need to do this. That is when I'm going to apply the reverse voltage, thyristor should turn off. Okay, that is, so inductor is taking the extra time to dissipate its energy what it is stored previously. So how to prevent or how to limit this, we will discuss in the next class with the concept of the freewheeling diode. So I will stop here. So next week we are having a test. So do the test well. That is a with video. You have to switch on the video. I think all of the faculties, I think most of all your mentors only they are allotted. So we have a 18 or 15 students per faculty and we will be monitoring. So that is, so how you are writing, so you have to, that is how you are writing the test. You should not copy, read it. So that is to make you that to prepare for the exam. Already the exam dates are announced. So you have to prepare for the exam. For that we are doing, that is you have to switch on your video and you have to write. Okay, thank you. I will end the class.